welcome to This Explainer. Look, we're just going to jump right in and confront a stark reality of marine engineering. When you are out on the open ocean, aboard an isolated structure packed with fuel and electricity, the stakes are literally astronomically high. Fire is consistently one of the most dangerous casualties a crew can face, and knowing how to fight it, well, it isn't just about passing some exam, it's about sheer survival. Because here's the thing, there is no fire department coming to your ship. If a fire breaks out, there's absolutely nowhere to run. The crew members, you, are the first responders, and honestly, you're the only responders. Everything we're going to look at today is built entirely around this intense, isolated reality. Okay, Section 1, the fire triangle. So a fire is not some invincible monster, right? It's just a chemical reaction. And like any chemical reaction, it has strict requirements. To even exist, a fire needs 3 things at the exact same time: heat, fuel, and oxygen. These make up the 3 sides of the fire triangle. The golden rule here is brilliantly simple. If you remove any single one of those elements, the fire mathematically and physically just dies. Every piece of equipment we've got is basically a specialized weapon designed to break one specific side of this triangle. You can really see how 3 totally different mechanisms lead to the exact same result. When you spray water, you're aggressively cooling the fire below its ignition temperature, so you break the heat side. When you lay down a thick blanket of foam, you're smothering the flames, completely cutting off the oxygen side. And if you just shut a fuel isolation valve, you're starving the fire, breaking the fuel side. 3 distinct actions, 1 life-saving outcome.
Moving on to Section 2, fire classes and the right weapons.
To actually fight a fire, we have to categorize the chaos. There are 5 specific classes of fire you might encounter on board. Class A is your ordinary combustibles, wood and paper in the accommodation areas. Class B is flammable liquids like fuel oil down in the machinery spaces. Class C covers gases, Class D is combustible metals, and Class E is energized electrical equipment. The absolute key here is matching your portable extinguisher to the exact material that's burning. You want water for Class A, but you need foam for Class B, and maybe dry powder for Class D. All right, let's test your instincts with a high-stakes scenario. Imagine you're down in the machinery space and an energized electrical switchboard, so a Class E fire, suddenly bursts into flames. What do you absolutely avoid grabbing? If you said water or foam, you just avoided a fatal mistake. You have to absolutely avoid water and foam here. Why? Because they conduct electricity. If you spray them onto a live panel, you instantly turn a fire hazard into a lethal electrocution hazard. Your very first step is to isolate the power, if you can safely do so. Then you use CO2 or dry powder, which puts out the flames without creating a conductive path straight back to your body. Section 3. Scaling up to fixed installations. Sometimes you're dealing with a fire that's just way too massive for a handheld tank, and that's where these huge fixed installations come in. They use the exact same principles as the handheld tools, just applied on a massive industrial scale. We've got automatic water sprinklers covering the accommodation areas. For huge machinery spaces or vehicle decks, we use high-expansion foam generators that pump out thousands of times their volume to smother a liquid fuel fire. And for places like cargo holds and engine rooms, we rely on CO2 total flooding systems. Let's take a closer look at that CO2 total flooding. It's an incredible system that completely floods an enclosed compartment with carbon dioxide gas. But while it is unbelievably effective, total flooding introduces a massive risk. See, CO2 puts out the fire by aggressively displacing the oxygen in the room. And naturally, a gas that displaces oxygen to kill a fire is going to do the exact same thing to a human being. It is a severe asphyxiation hazard. Because of that hazard, releasing a CO2 system isn't just a matter of pushing a button. It is a mandatory, strict, step-by-step survival protocol. First, you absolutely must evacuate all personnel and make sure everyone is accounted for. Second, you have to meticulously seal the space, closing fire dampers, doors, and stopping ventilation fans so the gas can't escape and fresh air can't get in. Only after flawless execution of these steps do you pull the trigger. It really is a one-shot attempt to save the ship. Let's pivot to Section 4, from suppression to prevention. To wrap your head around this massive shift in engineering, think back to a simple science experiment, putting a glass jar over a lit candle. The flame doesn't die because the air got cold, right? It dies because it rapidly consumed all the available oxygen trapped inside that jar, dropping below the threshold needed to keep burning. It's totally starved within seconds. And that exact idea brings us to the inert gas system, which is honestly one of the most vital safety systems on modern oil tankers. Instead of just waiting for a fire to start, this system continuously scrubs and pumps exhaust gas, mostly nitrogen and CO2, straight into the cargo tanks. It basically acts as a permanent ship-sized glass jar. Even when a tank is completely empty of oil, it stays filled with this inert, non-breathable gas. Just look at the math here. Standard atmospheric air is about 21% oxygen, and most hydrocarbon vapors need roughly 11% to sustain a fire. By keeping the oxygen levels inside those cargo tanks well below 8%, a spark physically cannot ignite a fire. It's literally prevention through total environmental control. Section 5. Early Detection and Strategy. Of course, all these incredible suppression systems are completely useless if you don't actually know a fire is there. The entire safety case for a ship depends on catching a fire in its earliest, smallest, and most controllable stage. We do this with an array of strategically placed sensors. Smoke detectors use dual ionization chambers to sense invisible combustion particles. Flame detectors look for ultraviolet or infrared radiation coming from actual flames. And heat detectors trigger an alarm if the room temperature just rises too fast. These sensors buy the crew the most precious resource in any emergency, which is time. When that alarm sounds, the crew has to flawlessly execute a 4-step survival strategy. First, locate the seat of the fire. Second, inform the bridge. You never ever try to fight a fire alone without telling anyone. Third, contain it. Remember, a fire exists in 3 dimensions, meaning it has 6 sides. You've got to close doors, stop fans, and isolate fuel to box it in completely. And finally, extinguish it, using the exact right agent for whatever class of fire you're dealing with. Wrapping up with Section 6, Mastering the Chemistry. Ultimately, survival at sea isn't about having the most water, it's about mastering the chemistry of your environment. Whether you're picking out a dry powder extinguisher or verifying a cargo tank is blanketed with inert gas, you aren't just a sailor or an engineer in that moment. You're a chemist, deliberately manipulating that fundamental fire triangle to keep your crew alive. I want to leave you with this thought to consider for your own safety readiness. A crisis at sea doesn't exactly offer a second chance to learn the rules. I really hope this explainer has completely changed how you look at the mechanics of fire and the incredible engineering designed to defeat it. Next time you find yourself in a high-stakes environment, will you know exactly which side of the triangle to break?